Oh, hello. I did not see you there. I was enjoying this beautiful beach behind me, but suddenly realized it's time to record this Lisa Symposium talk. So here we are. Today I'm going to tell you about quantum black hole seismology. So for the next 15 minutes, I'm going to try to convince you why this is an exciting topic. Should we all be excited about, and we should think about it as part of Lisa planning. Of course, you don't need me to tell you that we are in the golden age of black hole astrophysics. We've had a Nobel Prize which has been awarded for the discovery of gravitational waves. And we have this beautiful image of M87 supermassive black hole uh, at the center of M87. And that's also another great achievement pushing us towards the golden age of black hole astrophysics. But you also know that what makes black holes special is their event horizons. In fact, Event Horizon Telescope is named after this. And we all know that event horizons are special because the global structure of the space-time is different if there are event horizons. So if you are inside of the event horizon, then you cannot get out. You can all be crushed by the singularity. But if you're outside of it, you have a chance of escaping to infinity. However, we all learn at high school that in classical general relativity, local observers experience no drama as they cross the horizon. If you have a big enough black hole, nothing special happens if you cross the horizon. But we also know that there is something a little bit weird and wrong with horizons when you think about the quantum mechanical universe. So we have all heard about it in different forms. There is the infamous information paradox. The fact that unitarity of black hole evaporation cannot be consistent with local physics and a smooth horizon. So something with quantum mechanics or locality or the no drama or smoothness of horizon may go wrong. And this is known as the fireball paradox, at least in its latest incarnation. Less well known are the issues of quantum tunneling and quantum gravity. The idea is if black holes have a large entropy, even though probabilities of quantum tunneling for non-perturbative effects in quantum gravity are small, there are a lot of states you can tunnel to, and that means that the probability of non-perturbative or non-classical effects is of order 1. So there is a cancellation that happens. That suggests that when you form an event horizon, something non-perturbative may happen. And last but not least is the motivation of explaining dark energy through the scale of stellar black holes. That is a work we did more than 10 years ago now, suggesting that if you replace the horizon of a black hole by a quantum object, then you may explain the scale of dark energy. So with this introduction, one of the greatest surprises in the past few years, shortly after the discovery of gravitational waves by LIGO, was that you might expect signatures following the main event, the main major event, in the form of echoes that can be a smoking gun for the presence of a structure very near the event horizons. So the idea is an event like the famous 150914 that was observed by LIGO may look exactly as it's predicted by general relativity, but there are delayed effects due to near horizon structures. So if you have a membrane or a firewall or some quantum structure, there could be gravitational waves that otherwise would have fallen through the horizon that are reflected at least partially and can reach back to us. Now, since some of these waves could be, again, reflected by the angular momentum barrier, you actually form an echo chamber or a cavity, which could lead to multiple repeating echoes. And the time delay for these echoes is long, but only logarithmically long. If you imagine firewall is a Planck length outside the horizon. So for example, for 150914, this time scale is around 0.3 seconds. For supermassive black holes, the masses could be 1,000,000 times bigger. So you're talking about hundreds of thousands to millions of seconds, a order of a month, for example, as opposed to a order of a second. One way that we could think about echoes is a stimulated or excited emission. Now, we have a spontaneous emission. If you have an excited atom in vacuum, we know at some point it would decay to its ground state, and this is known as a spontaneous emission. For black holes, if you think of them as an excited state of matter, Hawking radiation can be thought of as a spontaneous emission. But if you follow that analogy, you could also have a stimulated emission. If you put a black hole in the background of gravitational waves or other waves, you could stimulate the decay, or you could get a stimulated Hawking emission. And then you can think of echoes as, in fact, a stimulated Hawking emission. So this is, in fact, an analogy that we made precise with my current PhD student, Qingwen Wang, and a current postdoc, Naritaka Oshita at Perimeter Institute. And in fact, we showed that reflectivity of horizon is given exactly by a Boltzmann factor, where T is the Hawking temperature, and omega is the frequency of the gravitational waves. So it's interesting that we now have, in fact, a prediction for how much reflection for echoes you expect as a function of frequency. And this is based on the thermodynamic properties of the black holes. In fact, if you push this analogy even further, you can think about echoes for LIGO and Virgo, or even for LISA, as analogous to Higgs to Large Hadron Collider. So they are both expected if you want your theories to be unitary in the quantum mechanical sense. They are both results of a requirement of a perturbative effective field theory. And the last analogy is that they are both required by the symmetries of the theory. On the left, for gravity, the symmetry is diffeomorphism invariance, which leads to holographic entropy. This is one of the requirements of the information paradox. And on the right, you have gauge symmetries of the Standard model that requires presence of a Higgs field. Of course, Higgs field is famously now discovered. The status for echoes is a little bit less certain at this point. So many of you may wonder, many of you have already heard things about this. Is there evidence for echoes in LIGO observations? I'm not going to give you a simple answer on this. We have a review article that I'm advertising here that you could read. And we have organized at least 2 conferences on this topic that you could go watch online. And the links to them you can find below here. And in short, the answer to the question I asked in the previous slide is that it is complicated. So finally, let me tell you about quantum black hole seismology, which is the interesting direction or interesting turn where we think the study of echoes is taking. And this is the work with, again, Naritaka, who I've already introduced, and Daichi Tsuna, who is a student at the University of Tokyo and a member of LIGO collaboration. So our papers are already out on this topic. And they are both published in Physical Review D. So what is black hole seismology? You might have heard about black hole spectroscopy or spectroscopy in general. So that's how you can learn about the structure of an atom or even the structure of a black hole. But usually when we talk about a spectroscopy of a black hole, you're thinking about quasi-normal modes that sit around the photon ring, far away from the horizon. However, when we think about seismology, for example, for Earth or for stars or for the sun, we're thinking about using waves that probe the inner structure of an astrophysical object, like Earth or our star. So we use that terminology to describe probing inner structure of a black hole, which is inevitably a quantum inner structure, since classical black holes don't really have any inner structure that can be probed from outside. And basically use that as a term to describe how we can learn about inside of the black hole by using at the spectrum or looking at the spectra of the modes of the black hole. So in our papers, then we looked at various properties of the quantum black holes and how they shows up in the spectrum of its excitations or spectrum of gravitational waves. So the properties that can be probed are reflectivity law of quantum horizon. So two possible reflectivity laws is a constant reflectivity or a Boltzmann reflectivity that I introduced to you. You see that on the left for constant reflectivity, you have this structure of the peaks, which are the harmonics of the echo cavity. On the right, you have the Boltzmann reflectivity, where the harmonics in fact peak around the horizon frequency for spinning black holes. So this peak you don't see on the left for constant reflectivity. For Boltzmann reflectivity, the harmonics that are closest to the superradiance frequency are enhanced. On the bottom, this is for m equal to 0, where superradiance frequency is not as 0. And what you see for Boltzmann is that the lower harmonics are enhanced, but for constant reflectivity, the lower harmonics are not enhanced. So by looking at which harmonics are excited, you can actually tell which law of reflectivity you're looking at and which harmonic you're looking at. And you could even read off the horizon temperature, or more exactly the quantum horizon temperature. You can learn about what type of object you're looking at. Is it an exotic compact object, or is it a modified dispersion relation? So the exotic compact object, there is a fixed reflecting surface, but for a modified dispersion relation, the position of the reflection of the wave can vary, can depend on the frequency. And that changes the structure of the peaks that you see in the frequency space. So in this case, you get like a fractal structure of the peaks near the superradiance frequency for modified dispersion relation. But for an exotic compact object, you get a simple peak. You could also learn about which overtones might be excited by studying the structure. You could also learn about the phase of the reflection, because that actually changes the peak frequencies of the harmonics. So different phases of reflection can actually shift the peaks of the harmonics, and based on exactly how much they are shifted, you can tell you what is the reflectivity phase or the phase of the reflectivity function. So more recently, this is an independent work we've been doing, almost finished, or by the time you see this talk, might have already been submitted, by Luis Longo, who is a student in Brazil, and Cecilia Chirenti, who's a professor there. And we've been looking at inspiralling extreme mass ratio systems, and how their echoes in fact depend on the mass ratio. So you could see here that in fact, as in the frequency time diagram, you see the main event plus these echoes. And in fact, by studying these echoes, you can learn about the temperature of the horizon, and also the amplitude of these echoes does depend on the mass ratio of the progenitors. So that not all echoes are created equal. Depending on the progenitors, echoes may actually look different. And this is this thing that we are studying in detail in this upcoming work. Finally, we actually found out that you could fit the data from a possible echo detection that we reported with Jahid Abedi in 2019 from binary neutron star major that presumably formed a black hole. And in fact, some of the reflectivity models, either constant or Boltzmann ratio with some properties, can in fact fit the echoes that we tentatively detected from in the aftermath of binary neutron star merger. You could even hope to detect failed supernovae from their echoes because their signal is different. You may not be able to see the signal itself, the signal of the formation of the black hole, but echoes may be visible because they actually have low frequency harmonics. So this is the example that I've given here for LIGO and Einstein telescope and Cosmic Explorer, where you could actually see them up to tens of megaparsecs and beyond, depending on the properties. Yeah, so you also hope to see echoes from LISA sources, not necessarily failed supernovae, but other types of exotic things that could happen. Because the echo signature is different from the GR signature, some things might be easier to be seen through their echoes as opposed to the GR signal. So let me conclude. Quantum black holes may be much more interesting than their classical counterparts. They may have logarithmically delayed echoes that appear in diverse contexts from quantum black holes. They may even show up in quantum information and in pandemics, although I didn't get to talk about that. There is tantalizing, though controversial hints for echoes in LIGO. Black hole seismology is a systematic way to probe quantum structural black holes using any gravitational wave detector, such as LIGO or LISA. And finally, let me leave you with this. Don't ask what echoes can do for you, ask what you can do for echoes. Thank you very much. I hope you enjoyed this presentation, and sorry for having gone over.